So this is what we, at the end of the hour, did yesterday. The root mean square velocity is calculated like this. This is probably the last thing you have written down. And remember, strangely, the molar mass needs to be converted to kilograms to be able to use it in this equation, because it has to cancel with the unit kilogram in the R. R is joules per mole Kelvin. This equation allows us to calculate how fast the particle, on average, the particles of a gas are moving. At room temperature, lighter gases move faster. If you notice this, the velocity is inversely related to the molar mass. So if you have a low molar mass, the particles move real fast. If you have a high molar mass, it's in the denominator, the particles move slow. We'll do a problem with this equation later this hour. For now, we're going to go in this direction. I'd like to just extend that ideal gas law just a couple of times. And this is something that you saw in Chem 1, so there's going to be no surprises or even enlightenment on this slide. We know that PV equals nRT, and we also know a relationship that involves moles. So there's two equations on the slide that have moles. There's the ideal gas law, and then the simple molar mass equation. Sometimes it's handy to have mass in the ideal gas law because you'll be given the mass of a gas. Or sometimes you have to find the molar mass of a gas using the ideal gas law. So it's good to have other versions of it. You don't necessarily have to, though. You could always use the ideal gas law, solve for moles, and then apply it to whatever context it needs. But if we took this equation and solved it for moles, remember moles is N, moles equal mass over molar mass. So there's something that we can plug into and substitute in the ideal gas law. We could also say that PV equals mass over molar mass times RT, just like PV equals N times RT. Because N and M over MM are the same thing. Now normally, we write the ideal gas law with nothing in the denominator, so more commonly, I guess, you'll see this. PV times molar mass equals mass times RT. This will be an equation that you'll use. You'll be able to use it doing some of the homework exercises, the practice test. If you're given the mass of a gas and you know what gas it is, you can solve for whatever variable they ask for. Now the other thing on the slide is to use density in the ideal gas law. You probably used density already last year too. Can you take this and express it in terms of density? Can you get density into that formula? And if you can get density into it, if you're bold and courageous, I'd like to invite you to come up and write it on the smartboard. Who's that? Who's that? Who's bold and courageous in here? Ah! We have one. Well, why don't you put it up on the board and then everybody can critique. I see what you did. Yeah, you did.
Oh, I forgot the N. Wait.
You replaced. I think you replaced. And yeah, right.
Yeah.
And then there's one more thing you can do. So you did great. This is awesome. You found the mass and you replaced it with dV, density times volume. Now, one other thing can be done with this, just to clean it up one more step. What is it? Yeah, get the V's out of there too, because you could have lost the V's. Just divide both sides by V and it'll be gone. Yeah? So, rather than erase, I'll just do this. P times molar mass, getting rid of that V and rid of that V, equals D RT. Yeah. The one thing I would say about this calculation, and I think you probably ought to remember this, is that density, it needs to be in the unit grams per liter, not grams per milliliter. We're used to using grams per milliliter for densities, but that's with solids and liquids. Those are condensed states of matter where the particles are packed together real tight. When the particles are spread far apart in a gas, you don't have much mass per milliliter. We actually go out to grams per liter to measure the mass, the density of gases. And you will need to use grams per liter because that set of units will be consistent with the R, and the units will cancel out the way they should. If you leave this in grams per milliliter, the volume won't cancel with the R. And make sure, by the way, when you use molar mass, it's grams per mole. Otherwise, the moles won't cancel from R. But we, I think, know that about grams per mole. We know that from the last lab that we did, 2 labs ago, when you had to find the molar mass of an unknown gas. If you didn't put grams per mole, you got caught. And so hopefully we've got that now in our brain. It's fresh. And by the way, I'm doing real well with grading your labs from the last time. And the labs are great. I'm so happy. I've gone through just about 2 full sections, hoping to get it back to you tomorrow. And I don't think I've had to mark one group down yet for inaccuracy. Everybody is within the accuracy parameter that I chose. I gave you plus or minus 10% from the concentration of peroxide that I had. And everybody's doing great with that. So not everybody's right on the concentration, but they're good. They're good. So I like that. It's real nice to grade. So now let's take on a problem like this. Now, I'm going to ask you not to do the problem. I don't want you to just stop and define all the variables or whatever. Would you just take a moment and read the question? All right, so you know what to do, right? This is not a big shocker. There's a bunch of numbers in there, but you can organize that and figure out. The question is, what is the new pressure? Would you be able to find the new pressure? Yeah, so that's why I'm going to say, let's not do the problem. But I do want to say a couple of things about this. This is a problem, like a typical gas law problem, in which variables are changing. Now, in Chem 1, you were given several gas laws. You got Boyle's law and Charles' law and then Gay-Lussac's law comparing pressure to temperature. But then you also had a combined gas law and then ultimately the ideal gas law. In this class, it's fine if you want to keep all those in your mind. I don't give you the formula, so if you want to just keep straight all the formulas, fine. And no problem, seriously. You're going to find, though, that the solution guide and the textbook will just ask you to remember the ideal gas law and then do everything from there. And so I just want to show you what that means, so that maybe you'll think, okay, well that's one that I would maybe want to adopt. And that's what I'm saying in parentheses on this. You can use the ideal gas law. Normally, you would use the ideal gas law when you have one set of conditions that aren't changing. And that's not what's happening here. Things are changing. We have a volume 1, 500 milliliters, and then the volume 2, it goes down to 25 milliliters. And the temperature goes from 30 degrees Celsius up to 820. So we're asked to find, we know the initial pressure, we're asked to find what the new pressure is. So if you just use the ideal gas law, you can. I'll show you what to do with it. Identify all the variables in the ideal gas law that are changing. What's changing up here? The volume is changing. We're given an initial and a final volume. The temperature is changing. Same thing, initial and final. And then the pressure changes too. We don't know what the final pressure is, but we know what the initial was, and we'll have to solve for the new pressure. So the pressure, volume, and temperature are all changing. The moles, though, are not changing. It doesn't say any place that more gas is pumped in or taken out, so the amount of gas is the same. It's constant. And R, of course, is constant anyway, so R doesn't change. So what this says to do is take all the changing things and put it on one side. So divide out the temperature to get it on the other side. PV over T equals NR. Right? Now, since the pressure times the volume divided by temperature is equal to a constant, that means if these things change, the new pressure times the new volume over the new temperature will still equal that same constant. This is how we can get the combined gas law. This P1V1 over T1 equals P2V2 over T2. So you can get all those other gas laws out of the ideal gas law. And you'll see, as you go through some of the problems and you look at the solution guide, they'll be doing this. And you just get used to it. One other thing I want to say about this, when you get an answer to these kinds of problems, look at your answer and make sure that it seems reasonable. Because if you do anything wrong mathematically, you should have something that stands out that makes you think, no, that can't be right. Let me give you an example of this. When we do this problem, we're going to get a final pressure. The answer to this question is about 51,000 torr. Does 51,000 torr seem like a reasonable answer for a pressure? You remember what standard pressure is? Atmospheric pressure? 760. Yeah. And so this gas gives us 51,000. That should, I hope, cause you to just evaluate, does that seem reasonable? But let's take a look at what happens in this problem. We have neon in a cylinder. The cylinder originally is 500 milliliters. That cylinder gets squashed down to 25 milliliters. That's quite a compression. I mean, neon is an ideal gas, generally, under normal conditions. But if you take that 500 and squash it down to 25, you're cramming those particles really tightly together. So that's going to cause the pressure to go way up. Not only that, but this container is going to get cooked from 30 degrees, and it's going to go up to 820 degrees. So not only are we compressing it to increase the pressure, we're also going to heat it up. And that should increase the pressure as well. So now when you see those two changes, does it seem reasonable that we should have an enormous pressure at the end? Well, yeah, now that you say it like that, it should. So do look at what's happening in the problem when you get your answer and make sure that it seems like it's reasonable. If you have subtle changes in your variables, then you're going to get a minor change for your answer. I would say this, by the way. Going from 500 down to 25 milliliters, that's a huge compression. Probably, it's like squashing it by 20 times, going from 20 milliliters down to 1. You're going to kind of endanger the neon in terms of it might liquefy with that much compression. I mean, that's quite a compression. So it might liquefy, but I think what they're doing in the problem is they're heating it up to keep it a gas. Because the hotter it is, you know, the faster the particles are moving, preventing them from sticking together. It sounds kind of like the reading quiz that we took. All right, so anyway, just wanted to mention that problem. Then we have this problem. This problem I will ask you also not to do, because if you read this one, go ahead and read it. You're asked for a density. We just came up with an equation for density. All you'd have to do is plug numbers in and solve for the unknown. The unknown is what is the density. Solve for D, you got everything else. So this one is kind of insulting to our intelligence. Let's not do that. Let's move on to something that we have to think for. How about a derivation? We can derive something. That's a good way to spend our time. No, what I want to do is, there's one more gas law in this chapter. So let's derive Graham's law of diffusion.